Greetings, peeps! Welcome to this supplementary edition of Charging with Electrostatics. Okay, so in class we discussed how objects can be charged. For example, the triboelectric series. So two objects are rubbed together and some of them prefer to be donors of electrons, others prefer to be acceptors of electrons, and therefore there's that separation of charge. Charge is always conserved. The total charge is constant, but some of that charge, in particular the electrons, will move from one substance to another. The protons stay at home. They stay fixed, bound to the nucleus. So, another thing we touched upon was that all charges are quantized, and the smallest possible charge is plus or minus 1.6 times 10 to the negative 19th coulombs. This was determined by the Millikan oil drop experiment. And the charges that we're talking about, of course, are protons with a positive charge, electrons with a negative charge, and they both have this same value of 1.6 times 10 to the negative 19th coulombs per particle. Two, we also determined that like charges repel. So if you have two positive charges, they're going to feel an electric force that repels them away from each other. Two like charges that are negative also will feel this repulsion. It just so happens that the accelerations will be much greater here due to the fact that electrons have a mass that is much, much smaller, about 1,800 times smaller than protons. So this would experience, for the same distance apart, the same acceleration. When we discuss Coulomb's law, which is a lot like universal gravitation, it's another inverse square law relationship, we'll see that that is indeed the case. And we'll see how strong this electrical force is. And of course, if charges are unlike, then they attract. The force electric would bring them together. And to repeat this, I can't repeat this often enough, I don't think, but in solid materials, the electrons can either move or be transferred, while protons are tightly bound to the nucleus. And they stay put! Blah, 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 blah. They stay put. So, so important. If you want a net negative charge, it means that extra electrons, negative charges, have moved in. And for something that has a net positive charge, where positives outnumber the negatives, all that means is that the negatives moved out. It's not that positives moved in. This is a solid substance we're talking about here. But that the net positive charge means that negatives moved away, leaving behind more positives in that region. Okay, next we'll talk about charging, different techniques for charging other than the triboelectric technique, which is by friction. Hey peeps, look at a charging technique known as charging by conduction, which is by contact. Very simple method. Now, we mentioned triboelectric charging by friction, so let's assume for a moment that we have an insulator. And an insulator is something that doesn't allow electrons to flow through the material, but you can charge the surface through triboelectric action for sure. So in this case, the PVC was charged by friction. In this case, maybe rubbing it with rabbit fur. The PVC then gains electrons. Here's the insulator, and it's got negative charges on it. Secondarily, we have a conductive sphere that is neutral. So materials that are conductive allow electrons to flow through. Metals are terrific conductors of electrons, and so that's why we use them so much in electricity for being a conduit. Essentially, wires are conduit for electrons moving through that wire. And so this is neutral. At the moment, there's no net charge on this conductive sphere. But what happens when we bring said PVC tube near the conductive sphere? Well, the PVC is brought near it, and the electrons in the sphere, which again are allowed to move, go to the other side. They're pushed to the other side because they're being repelled. And there is this attraction also between the positives that are left behind and the negative PVC rod. So in this case, though, I want to be clear that we do get this effect of polarization. We get the negatives on the away side to the right and positives on the left side. But there has been no transfer of charge. So the net charge, if we were to add up all the negatives and positives, it still would be equal, and this would be still neutral, but polarized. However, what happens when contact is made? When contact is made, then there's this transfer of charge. The negatives from so these electrons here from the PVC will move into the conductive sphere, and this will gain a few electrons. So they're transferred to the sphere, and the sphere now has extra electrons, making it net negative. PVC is still negative, just a little less negative, that's all. So its outlook is a little brighter. Now, in number 5, we see that the PVC tube has been moved away. And there is no outside charge present, and the charges inside here will then distribute themselves evenly. So they repel each other kind of in this, that's not kind of, it's exactly what they do. They repel each other so that they spread out as far away as possible, and that's why they spread evenly across the surface of the sphere. And so that's charging by conduction. It's that idea that there's contact and a transfer of charge and leaving a net charge behind. You can imagine that this would be done the other way. If this were a positive charge over here, these would be reversed, these charges, and what we'd have is electrons moving onto the positive rod, making this more net positive. So that would be the case for where we have a net positive charge. Here, clearly this is contact, a direct transfer of charge through contact. Next, we'll look at something called charging by induction, which includes this interesting concept called grounding, which I'll try to explain as we go along. Zip. Charging by induction, where there's no direct contact between the charge object and the object that's going to be charged, which is, again, a conductive sphere. So here we've got a neutral conductive sphere connected to electrical ground. And so what ground means is that this is connected to a vast, vast reservoir of electrons. And so what that means is that it can either absorb excess electrons and give them a path to escape, or it can provide a path for the electrons to get back in. The idea is that this thing likes to neutralize the situation. So in other words, if you want a neutral sphere, you connect it to ground, and if it was positive, electrons stream in. If it was negative, electrons stream out, and everybody's happy because nature likes the neutral stance. All right, here's our situation though. We now have this PVC tube. It's negatively charged, and so we note that the negatives get pushed to the far side, but now they have a path to leave. So some of them are jetting out into this ground. There may be a few like hanging out on the edge over here, but a lot of them want to leave the ground. And we do note that this side becomes more positive as a result of those electrons abandoning over here. So the negatively charged PVC brought near does not touch the sphere. Be very clear about it. It's not touching. But now the electrons have a path to escape into ground. Now, the ground is cut. Zap. So the PVC tube is still near, though. That's kind of key, that this is cut while the PVC tube is still near. So what happened is that the electrons that left through the ground have been stranded. They can't get back in. There's no path for them to move. They have to move through some kind of conductor. So this has got a conductor to ground. They can't get back. So there's a couple guys that are like, okay, so now what happens? Well, this is now we have more positives than negatives in here, and moving the PVC away, and there are no outside charges present, the electrons then will move and distribute. So these guys kind of cancel out whatever they can, but it appears though that the positives have moved and redistributed. They have not. It's the electrons in the system that only do the moving, but it gives us this even distribution though of positive charge. So what's interesting about this is that we started off with a negative rod over here, and we actually induced an opposite charge. A positive charge is what we ended up with on the conductive sphere. So you might imagine that if this were positive, the opposite would occur, and that's true, that instead of streaming out, the extra electrons would be coming in. You cut the ground, and in that case, they're stranded inside the system for a net negative. So you can always think of it in terms of the reverse as well. Just recall that it's the electrons that do the moving. So here we got our net positive conductive sphere as a result of bringing in a negative rod and using this idea called the ground. So grounding will neutralize a conductor if it's left alone. So if I wanted to neutralize this, I would connect it to ground, which could be like your finger, actually. Zap, okay. Sometimes there's a zap, but usually it's not so bad for objects that have very little charge. And in this case, the electrons would come in from my finger and neutralize that over there. So how do you ground or neutralize an insulator? That's an interesting thought. Well, an insulator only has the charged parts that have been in contact with something else, or triboelectrically, there's that rubbing so that it has charge in a particular location. So you would just try to use maybe a metal or something like that and touch just the spots that have the charge. You have to touch all the spots on that object for the PVC. I'd have to touch it here, 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 here. Whereas in a conductor, you can just connect this anywhere and the electrons will flow into that kind of like a funnel. But here, yeah, you'd have to touch every little piece, or you let the environment do its thing. Turns out that electrostatics don't work very well when it's humid. So when it's humid, actually it's the water molecules that are polar, and they actually would start to neutralize this situation much more quickly. So it's kind of why we're not saving this topic for the very end. We're doing it now in part because we still have fairly dry air, and it's a good time of year to do that. And much later, and we could run into situations where the electrostatic or static electricity as you know it doesn't really work as well. So that's what it is. We got one more frame, and that would be talking about polarization of an insulated surface and what happens in that case. Bet you thought that was my mouth. Nope, nope. My mouth isn't that clammy. So this is clam. So it would be not as clammy as a clam. Right, because it's... So, polarization. Here, frame one, we have... Did I erase anything? No. Insulator with polar molecules in a random configuration. In other words, this is a net neutral situation. So polar molecules are just molecules that have the ability to have a side that's a little more negative. The electrons hang out on that side a little more than the other side. So there's some geometric configuration of the molecule that allows that. Water being a great example of a molecule, because water goes like this. It has an angle, and you know it's got the positives and negatives, and so it actually, due to its shape, is polar. And so many molecules are polar, not all of them, but quite a few. And so let's say that's on a surface, like we're gonna have you test it out in a lab anyway. So this is neutral because they're just kind of any which way, and they all cancel each other out as a result. Now, the activity is only on the surface here of this insulator. So if we now bring a PVC tube that's charged negatively near the surface, what happens is that those molecules, which have one side slightly negative, one side slightly positive, will then pivot. So there's this pivoting. They're all aligned. These little dominoes here with the plus minus are just a visual aid to explain what happens to the molecule. They obviously don't look like little bars and with pluses and minuses. That's just to represent the orientation of the molecule, which is much more complex than that in its actual shape. But so we have these all aligned because of the presence of these negative charges here. Notice that the negatives are going to pivot away. So the negatives move away from a negative charge because they get repelled, and the positives are happy to attract to this. So there's a little bit of an attraction between the positives here and the negatives here. And so that's how it corresponds in this surface. So these don't leave the surface, they're insulators, so they're stuck here, they can't move, but it's just that pivot of the molecules that occurs for this type of substance. Now, what about the situation here where I think you've seen, if we have very light objects of low mass, like little bits of paper or leaves or something like feathers, and you have that charged PVC tube here, then what we might have is that the molecules also pivot so that the negative side is away from this negative over here, and the electric force may be strong enough to actually work against gravity. Electric force actually is pretty strong, as we'll note. It can actually work against gravity, so shoom, they come up here, and shoom, they come up here due to electrical force, and they may stick and stay and hang out for a while. But it's possible, though, if there's a little bit of friction, there's an opportunity for the transfer of one of these negative charges into here. Well, if that occurs, then of course there's a net negative on this little piece of paper, and shoom, it flies off. It doesn't fall off, it just goes boom, like that. So they assume a like charge. This is a negative and that's a negative, and therefore they repel, and the electric force is pushing away, and they get repelled, and shoom, that's it. So that's polarization. Those are the different types of charging that we'll deal with in labs and in this unit. So notice that there was no math, right? So there's a lot of concepts here that we're going to go through, and it's a very important development in this unit for electrostatics, but also coming up for circuits. This kind of lays the groundwork. So hope I got it all in there. I went as fast as I can. So that's what it is, and we'll call it good. So, Morad, out. Those are my knees.